When we talk about living things, we think about ourselves, our pets, every type of animal that you could imagine, as well as trees and plants. But plastics? Some polymers are formed by a process called living polymerization. It's not living in the strictest sense of the word, but you'll see why soon. Living polymerization is a type of anionic addition polymerization, whereby monomers join together to form long chains of repeating units known as polymers. This requires a very reactive, unstabilized and non-conjugated nucleophile, in this case propyolithium, which is added to the monomers, initiating a reaction by adding to the double bond and creating a negatively charged carbon. This initiation step happens much faster than the following propagation step, and so every nucleophile begins the formation of a polymer chain. It is important the carbanion can be stabilized by electron withdrawing groups. In this example, the ester substrate has a -m effect on the negatively charged carbon, distributing the negative charge over the molecule and making the molecule more energetically accessible. The propagation step, whereby the monomers join to each other, is rather like the initiation step, but instead of the nucleophile adding across the double bond, it's the negatively charged carbon. Propagation occurs at an average rate, allowing chemists to predict and control the way polymers grow, synthesizing very well-defined polymers of almost, if not completely equal lengths, a property called monodisperity. What's special about this type of polymerization is that the active site remains active even after the reaction has gone to completion and all the monomer has been consumed, and this is why it's said to be living. This is unlike other polymerization methods, as they usually include a self-termination step or steps. This allows for two different outcomes. A solvent or electrophile, such as water, could be added to the mixture. This would protonate the active site, neutralizing the negative carbon, and would hence terminate the reaction. The second outcome is a lot more interesting. Instead of terminating the reaction, the addition of another type of monomer would cause the reaction to proceed as it did in the earlier propagation steps. This would form a polymer made of two different monomers with different properties to each other. This is called a block copolymer and will have a blend of characteristics from the two different monomers. But why is all this useful? Polymers have uses across the spectrum of science, but we're going to focus on its uses in the field of nanomedicine. Firstly though, what does nanomedicine mean? Nano means 10 to the power of -9, and in this context it's referring to size in meters, and medicine, according to the dictionary, is the art or science of treating disease with drugs or other curative substances, and so together we're talking about drugs and other substances that are 1/1000th of a meter in size. That's smaller than the width of a strand of hair. This could revolutionise modern medicine, providing new ways to tackle disease and illness, and possibilities for potential cures to paralysis and other disabilities. Everything from aiding drug synthesis to internal drug delivery systems, from adhesives that may seal punctured lungs to pioneering work on stem cell research, it's all polymers. Recently, scientists have discovered that it is the tiny hairs on the bottom of a gecko's foot that allow it to stick to walls so efficiently. So this idea was taken on by Professor Robert Langer and his research group from the Massachusetts Institute of Technology, a person who features very frequently in the field of biomaterials and nanomedical polymers, and his achievements and progress in these fields have been recognised and awarded by the global scientific community on numerous occasions, and it won't be the last of them you hear in this video. He and his colleagues designed an adhesive made from polyglycerol co-sebacate acrylate, PGSA for short, that resembles the hairs on the gecko's foot, partly to do with its chemistry and partly to do with the way it's moulded. This works well in wet environments, for example inside the body. It's biocompatible, so it won't cause irritation to the body, and is biodegradable, so it dissolves once the wound it has been sealing has recovered. This is a much better and much easier alternative to present methods, including staples and stitches, to close wounds post-surgery. Research is also ongoing to try and create a real and working Spider-Man costume using the same polymer technology, so who knows how long it could be until you're scaling up the side of buildings like your favourite superhero. PGSA and or PGLA, polyglycolic cholactic acid, has another use in the world of nanomedicine, and in my opinion this one is even more incredible than gecko glue. It, mixed with a bit of technical stem cell research, is a potential cure for paralysis. What you're about to see is a mouse whose spine has been broken, and then you'll see the exact same mouse after treatment. You can see now the mouse is clearly dragging its back legs, and then after treatment, the mouse has almost full use of its legs. Movement isn't completely natural in the mouse's hind legs, but I'm sure you can appreciate what a difference the surgery has made. This technology is now in human clinical trials, so it might not be long until permanent paralysis is a thing of the past. But how does all this work, and what does it have to do with polymers? Robert Langer reports that PGSA or PGLA form a polymer scaffolding which also stimulates the growth of stem cell tissue, in this case axons. These allow nerve impulses to pass through previously damaged tissue, transmitting and receiving information to and from the spinal cord and brain, allowing the patient to regain feeling and hence movement in their previously paralysed limbs. PGSA and PGLA are chosen mainly for their porous properties and biocompatibility, but also for their glass transition temperature of approximately 40 degrees Celsius, the temperature at which the polymer goes from being a glass to be behaving like a rubber, allowing the scaffold some flexibility if excess force is exerted on it. Drug delivery systems are another speciality of copolymers. These have many advantages because the copolymer can be finely tuned and synthesized to have exactly the desired characteristics. These include that they have a homing device, usually an antibody, allowing the drug to target and attack only the disease or tumour. Soluble, so it is easily dissolved in the bloodstream. Degradable, so once the polymer has been used it does not remain in the body. It should also be resistant to macrophages, so it is not easily removed from the body before its use, as the body tries to eject and excrete foreign particles as part of its immune system, and it must also be able to encapsulate the drug that it will carry. Also, because of their extremely small size, they will not clot the bloodstream, and will be able to get into diseased tissue more easily. Each block or polymer is chosen carefully to make the copolymer to specification. What does the future hold for nanomedicine? In short, a lot. Nanomedicine is a relatively new technology, and scientists claim that they have only scratched the surface of the novel concept. With the world's top governments dedicating millions of pounds for research into one of the most increasingly popular medical research fields, discoveries are being made frequently, but who knows what its limit is. When we look back through time, we have had the Stone Age, the Bronze Age, the Iron Age, each of which becomes more technologically advanced from the one which precedes it. So perhaps after this video you'll understand why the age in which we live in today is often referred to as the Polymer Age. Thank you for watching.